Right?
Yeah.
Okay. So let me share the screen. All right. Can you guys see the presentation?
Mhm.
Yes.
Okay. Give me one sec. Uh, okay. All right. Good afternoon, everyone. My name is Nikhil Sridhar. I'm an undergraduate student majoring in computer science. My presentation is on a paper called Towards Robust General Medical Image Segmentation. So the motivation of this research behind this paper is to explore the realm of adversarial perturbations, or in other words, we can define perturbation as noisy changes made to the input data that machine learning models and systems utilize. So the main significance behind this research is to reliably and effectively test the resistance or robustness of machine learning systems to attacks. And one form of an attack would be adversarial data perturbations. So as you can guess, metrics regarding successful defenses against possible threats to machine learning systems, and in our case, to the input data to those systems, is a metric that is just as significant at determining robustness for a deep learning system as loss or accuracy metrics are. So some solutions to this realm involve implementing attack strategies as well as defense strategies to improve the resistance to adversarial perturbations in deep neural network models. However, since this is a relatively recent field, as indicated in this paper, there's still a lot left to be explored. Okay, so the problem statement, or the main question that the authors seek to explore, is how can the robustness of general medical image segmentation systems against adversarial perturbations to input data be assessed? Some reasons as to why this problem is worth considering is that, again, the robustness of these systems against adversarial perturbations should be one more dimension of importance when validating the effectiveness of a deep learning model. Other reasons involve the fact that this area of medical imaging and deep learning is a relatively recent one, which also means there's a lot left to discover. Because of that, the area is rapidly gaining interest from both novices as well as experts within the deep learning community. So for those reasons, we can start to understand why this is a rather relevant and practical problem to be researched. Other reasons for why the problem is important is that according to the paper, it's highly likely that the vulnerability of deep learning methods in the medical domain to adversarial attacks has been underestimated. So this means that models can be altered and tampered with by certain unapparent attacks and additions of noise to input data. This can make it apparent that the model being used is has some brittle and weak parts when it comes to defending against input data perturbations. And this behavior of this input data perturbations has been studied for various tasks like detection, classification, as well as segmentation. However, the main takeaway from the solutions to this problem is to reliably develop and assess robust deep learning systems in the medical domain. Okay, so as for the main contributions that this particular paper brings, there are two major contributions. The first one is a proposal of a benchmark that the authors claim evaluates robustness in the context of the medical segmentation decathlon, or we'll abbreviate as MSD. This MSD is a crowdsourced challenge of general semantic segmentation algorithms that was held during the 2018 MCCAI conference. So they proposed this benchmark by extending this recent framework called AutoAttack to the volumetric data segmentation domain. To briefly elaborate and possibly dispel any confusion, this AutoAttack framework, it's a natural image classification framework. It's parameter free. It's computationally affordable. Uh, Basically, it's a user independent ensemble of attacks to sort of estimate adversarial robustness. So that's the first contribution. The second contribution is that the authors actually present a novel like lattice architecture for robust general medical image segmentation. They call it ROG. We'll just abbreviate it as ROG. Um, this ROG architecture is capable of segmenting organs as well as lesions on MRI and CT scans. And the authors actually claim that this architecture is the first generic medical image segmentation model that's robust against adversarial perturbations. Okay, so moving on to the outline of the proposed approach, the methodologies that the authors illustrate in this paper can be broken down into like three main categories. The first one is extending auto attack to 3D segmentation. Second is adversarial training, and the third is general medical segmentation. So the first one, the outline of extending auto attack to 3D segmentation, can be explained by first understanding the traditional usage of auto attack. So they state that auto attack is used to trick models that assign a distribution of probabilities to each image. However, the authors are interested in attacking models that assign a probability distribution to each spatial location, as opposed to the traditional usage of auto attack. So what they do is they alter the definition of attacks to meet their interests and usage of auto attack. We'll discuss more details on this in the following slides, but now for the outline of adversarial training. This is the main metric they use to improve the robustness of their ROG architecture. They call it free adversarial training. So this method is applied to the task domain, and in our case with the authors, they use it for segmentation tasks and to better fine-tune the models that they use. Okay, the outline of the general medical segmentation category is to use their ROG architecture as an efficient model for robust generic segmentation. This exploits increasingly larger receptive fields while also preserving high resolution features. Existing methods in this area actually kind of lack resources and domain training of multiple models, which can be computationally expensive and lead to high computational demand for this adversarial training area. So therefore, the strategy of exploiting this growing receptive fields while maintaining high resolution features that ROG kind of utilizes is pretty important and effective. Okay, so moving on to the further details of the proposed approaches, starting with extending auto attack to 3D segmentation. To break down what auto attack is mainly composed of, it's composed of four parts, which are auto projected gradient descent cross entropy, auto projected gradient descent difference of logits ratio. Third is targeted fast adaptive boundary, and fourth is square attack. So the first two auto projected gradient descent components, or we'll just abbreviate to PGD. So these first two auto PGD components are adversaries responsible for optimizing the ratio of cross entropy to difference of logits. Targeted fast adaptive boundary is this method that minimizes decision changing perturbations. And square attack is a score based black box attack. So since the authors are, or they indicate that they are interested in auto attack for its ability to attack models that assign a probability distribution to each spatial location, the authors actually defined attacks to consider inputs and outputs as four-dimensional tensors, where there are three spatial dimensions plus the channels, as well as the spatial dimensions and the probability distribution over the classes. For the attacks to succeed, success is actually defined as whichever state that the model has been tricked or fooled by the attack when it comes to classification tasks. But with segmentation tasks, the authors redefined success as some drop in the dice score below half of the average performance in the ith task over clean images. All right, so moving on to the details regarding the ROG architecture. So this architecture is arranged as like this triangular lattice-like arrangement. it's composed of uh, processing nodes, which are those little green circles, and then on the top we have on the top left we have an initial module that takes in the input, and the top right we have the segmentation head, which returns the output. So each processing node is connected to the upper and lower level processing nodes, as you can see. The architecture doesn't use any dense connections, which obviously results in fewer parameters and better efficiency. And we can see that that L parameter, where it says L equals 2. So this L parameter actually represents the number of nodes in the last scale. So the authors observed that smaller values of L benefited smaller objects, whereas larger values of L benefited larger objects. Also, inside each node, there are two separable convolutions, instance normalization layers, as well as residual connections. The authors use something called swish activations because of its smooth gradient, which the authors also claim is beneficial to adversarial training. All nodes connect to the upper and lower levels using 1 by 1 by 1 convolutions to adjust the number of feature maps. The authors also state that they change the spatial resolution by either using a stride of 2 or adding some method called trilinear interpolation, which is a method to approximate the value of an intermediate point in a 3D grid by values of adjacent lattice points. We'll actually come back to this later. ROG automatically adjusts to each task by using the average size of the volumes in the dataset to select the input patch size, as well as the strides in the initial module and the upsampling factors in the segmentation head. All right, so for the authors' experimentation, their experimentation consisted of two things. The first is called adversarial robustness assessment, and the second was just general medical segmentation tasks. The first, we'll start with the adversarial robustness assessment. The authors state that they used two variants of the ROG architecture and trained those two variants for clean image tasks as well as free adversarial training, respectively. After that, they used the extended versions of AutoAttack to attack the models. The authors also stated that for the auto projected gradient descent, or PGD, and fast adaptive boundary attacks, they fixed the number of iterations to 5, and the strength of their attacks fluctuated between 5 out of 255 and 16 out of 255 in order to assess the robustness metrics of each model with respect to different strengths of perturbations. And for the square attack, the number of queries also fluctuated between 500 and 5,000. And the models trained on 80% of the data set and were validated on the remaining 20%. The authors made design choices regarding the results over pancreas and prostate segmentation tasks of the MSD. Finally, they evaluated the robustness of another architecture called NN-UNet, which they claim was a competing architecture to ROG and the top performer on the MSD. Okay, so for the second part of their experimentation, which was generic medical segmentation, they evaluated the generalization capacity of ROG on the MSD. Each task had one organ or one tumor, and source data was either CT or MRI scans with single or multiple modalities. The authors also stated that the number of patients fluctuated between 30 and 750, with a total of 2,633 volumes. They used an atom optimizer with a weight decay of 10 to the negative 5th power. Their initial learning rate was 10 to the negative 3rd power, and for every 50 epochs of no improvement monitoring validation loss, they reduced the learning rate by a factor of 1/2. Their optimization loss function was a combination of dice loss and cross entropy loss. Finally, they state that they use data augmentation, which consisted of random like rotation, scaling, mirroring, and other sort of transformations. And in order to handle like data imbalances, they state that they sampled cubic patches with a 50% chance of being centered at a foreground category. Okay, so for the results of the experimentation, for the first part, the adversarial robustness assessment, the authors found that when comparing the performance of the PGD and the auto PGD cross entropy methods, the second one, the auto PGD cross entropy method, performed a lot better for every attack strength specified. So we can observe from the table in the lower diagram that the PGD based adversaries are shown to be the strongest attacks. We can also see that the score for the clean images and the score for the targeted fast adaptive boundary method are the same, which is like FABT and clean. This can suggest that targeted fast adaptive boundary may not be the best for segmentation tasks. We can also observe that the 10 graphs below actually come from the MSD. They depict the adversarial robustness for the 10 tasks in the MSD. Furthermore, ROG was trained on clean images, which is represented by the dotted line in the graphs, and it was also trained with free adversarial training, which is represented by the solid lines. So the adversarial robustness for both models was evaluated at different values of the strength metric, which is epsilon. Each color represents different classes per task. The results show that the training with free adversarial training actually enhances the adversarial robustness against attacks, which fortunately supports the findings and approaches that the authors devised. The authors also note that free adversarial training doesn't actually cost much in performance on clean samples, and the improvement in robustness is actually larger for bigger structures like the lungs or the liver, or for more definite structures like, as mentioned, the left atrium of the heart. Okay, so continuing with the results, the authors also found that ROG was superior to the previously mentioned NN-UNet architecture on liver images and with the presence of adversarial noise. They also state that this NN-UNet architecture fails on both false positives and false negatives. And since ROG doesn't suffer from these mistakes as much, they state that ROG can be viewed as a better solution for the task or the challenge of reliably robust general medical image segmentation solutions. ROG also suppressed other well-known models such as this one called MP-UNet in a clean setup, while also containing around 24 times less parameters. It's obviously a lot more efficient. And since NN-UNet uses an ensemble of models, and ROG relies on just one architecture, it's obvious as to why ROG might be more efficient. Another competing network, the fourth one we see is C2FNAS. This one actually also is a single fixed architecture like ROG, but still it required around 5 times more gigaflops, a lot more parameters. So when considering the high expenses of studying this dimension of adversarial robustness, it can be concluded that maybe utilizing ROG as a baseline might be advantageous because of its efficiency and relatively strong accuracy and robustness. All right, so some related works involve many studies and research regarding solutions when it comes to this problem of adversarial robustness in deep learning models. So the studies referenced all explore different adversarial attacks and defenses for deep learning models. The authors state that these studies made decent progress, but as they also state, considering the little amount of explored content in the area, there's still a lot left to explore. Other related studies regard the vulnerability of deep learning methods in the medical domain, where the studies show that the vulnerability of medical image segmentation models and systems is underestimated. Okay, so in conclusion, this paper it does a good job of presenting relevant methods to assess robustness of deep learning models within the medical domain against adversarial perturbations and attacks. So the authors also found that the two PGD-based adversaries offered the strongest attacks, which provided a good assessment of the robustness of the ROG architecture they devised, since a good basis of attack strengths were used. We can also see that the ROG method they came up with outperforms what they claim is the state-of-the-art methods in this dimension of deep learning. We can see that ROG outperforms the competing MPUNet, NNUNet, and the C2FNAS networks or models when it came to efficiency, robustness, or even both. ROG was a pretty competent method when performed over clean images in most tasks of the MSD, while performing better than one of the highest performing benchmarks under the adversarial attacks dimension. So regarding these findings, it's safe to say that ROG provides a good, strong novel baseline method and can be used as a tool to conduct further research and develop better solutions in this area of deep learning. Okay, so for strengths and weaknesses, this paper demonstrates a few key strengths and weaknesses actually. Starting off with the strengths, it's clear that the authors proposed a pretty novel method, and this method serves as a good baseline metric for future research. This is especially good when considering the novelty of this area, as they mentioned, because there hasn't been much done. But the fact that the authors were able to propose a strong enough solution to this relatively new and unexplored problem is pretty good. Another strength is that the problem explored by the authors is, I believe it's a practical problem, and one that's worth the time and resources to explore, because adversarial attacks to data and models can obviously pose a threat to not only the legitimacy, but I guess the future use of the deep learning system that is in question, and it should be taken seriously, like loss, accuracy, as well as efficiency metrics. Third, the experimentation was pretty deep and consisted of enough substance to effectively assess the robustness of the ROG architecture that they devised. The results from the experimentation actually supported the proposed approach and demonstrated the effectiveness of the ROG architecture in segmentation tasks against adversarial noise, as well as with clean images. It outperformed the state-of-the-art methods in one way or another, so that was good. And finally, the overall structure, I thought the overall structure of the paper was pretty comprehensive and complete. The authors showed a strong attention to detail. They had deep explanations in a meaningful way without large amounts of confusion or complexity. Okay, so that being said, those are the strengths. Now we can get to the weaknesses. The first weaknesses is that some terms, details, or even whole processes such as auto attack, trilinear interpolation, or switch connections weren't really defined or even introduced within the paper. They were simply just referenced to other papers that are more in depth. But to be honest, I don't believe this is a good idea when writing papers like this, because I think the authors of papers should at least briefly, they don't have to go in depth, but at least briefly introduce a topic enough to the point where future references to the topic within the paper won't confuse the reader. But because of this, the paper had some ambiguous and confusing moments when reading it. Another weakness is that the paper lacked visuals. There were only one or two diagrams of the architectures that the authors mentioned, and those diagrams were either not detailed enough or don't have captions that further explain the details of the diagram. The authors kind of only included one diagram for ROG, and for auto attack, although being a large framework, they didn't even have a diagram to help the reader visualize how it works. So that was a pretty big weakness. Another weakness is that I thought the conclusion of the paper lacked depth, and it provided very vague future directions. Now, considering how new the field is, the author should have at least been a bit specific on future directions, since they said there is a lot to be explored. Also, the authors in the conclusion didn't really recap everything they had found and achieved from the study, and didn't use the findings to kind of argue how their problem should be seen as practical. Um, Finally, similar to the last points I've just mentioned, there's no elaborate explanation or suggestions for future research paths and directions. Okay. Um, so for the overall rating of the paper, I gave this paper a 2, based on the NIPS system. Although I think it's a little bit high. I thought the paper proposed a pretty viable solution to a practical problem within this field of deep learning and medical imaging. And that this paper supported the concept that a strong and good deep learning model should be fast, accurate, scalable, and efficient, as well as robust to adversarial perturbations. The paper also presented a decent baseline method in a relatively new and growing area of deep learning. Uh, However, because of the weaknesses mentioned, the paper, in my point of view, fails to attain a higher rating. It's just a bit intuitively challenging to understand how some methods like AutoAttack worked and what certain terms, like they mentioned, trilinear interpolation and Swiss connections meant, without any background or context of these terms and methods. Obviously, if the paper addressed these weaknesses, the rating would have been higher. But I still maintain the perspective that this paper proposes a novel solution to a relevant problem in the field of medical imaging. All right. So some future directions I thought of after reading this paper regarding this area, and based on the findings of what the authors came up with, are to, for one, compare robustness against adversarial attacks with a multitude of other models and architectures, and like extrapolate and find and provide more findings and provide more explanations and I guess kind of provide more insights. Um, Another possible direction is to identify weaknesses of ROG and implement sort of an updated, improved version and perform more experiments to support the upgraded version. One more idea is to conduct similar studies at different scales, like cellular or microcellular, or even larger scales, to assess the robustness of the architecture across multitudes of object sizes to see if adversarial robustness is improved for larger or smaller objects. And one more idea is to weight and compare against more state-of-the-art methods when they come out, to ensure like continued effects and potency of the model, to see if there are any modifications that can be done to further update the model. All right, and that concludes my presentation of the Towards Robust General Medical Image Segmentation paper. Looks like I might be a bit off schedule. I apologize for that, but I hope everyone enjoyed. Any questions or comments?
Yeah, great. Thank you, Nikhil, for the great presentation. I think you did a wonderful job, discussing all these details. Yeah, I like the analysis you presented. Very thorough in terms of weakness.
Thank you very much, Professor.
And the future directions. Yeah. Okay. So any questions from the student? So this is the time for you to participate the discussion.
I have one question.
Sure, go ahead.
So I get why adversarial learning is important more generally to the field of computer vision, specifically just like smoothing out functions, because there's these gaps in, say, like classification outputs. But specifically with medical imaging, it seems like I don't quite understand what's a situation in which you care about the adversarial robustness. Like, when are you going to have someone maliciously perturb an image?
Well, that could happen, right? Like it's definitely not impossible if that happens. Um, but like it should like I mentioned, a good network, or not a good network, a good system should like be fast, scalable, accurate, efficient. But like if someone is just able to, just add some noise and kind of mess up your system, kind of like demonstrates, right? Like it should be a little bit more robust towards that.
Yeah, maybe I can give you a maybe a more concrete example. So I think there's a lot of telemedicine, right? So there's a like a startup like Teladoc. Obviously, they are doing this kind of remote telemedicine, but there's also similar, like you have a, let's say you have a medical app, right, application. So you can, just for the, very convenient use, right? Maybe you have some skin issue, right? You can take a picture, right? And then the app will run some AI or medical AI algorithm, right, to run some diagnosis, right? So if then here the adversarial robustness is going to be very important, right? If there's a malicious attacker, right, has some way to hack into the app and somehow, adding some perturbation to the user data, right, which you wouldn't notice any difference just looking at the image, right, but give you a totally different diagnosis, right? Say
I see.
then
That's a good example.
you're right. So then you give you like the false diagnosis, then this is gonna be problematic, right? So this is just like one application. Also, I think in my lecture, when I talk about adversarial robustness, there's a paper also showing a very good demo, right? They were able to hijack or injecting noise into the CT scan, right? CT scan, those are the 3D volume. They are injecting like nodules in the lung. So overall, they are generate some malicious or perturbate data and to make the physician to misdiagnosis for the patient. So yeah, so these are some of the potential high risk in the medical domain. And because of these kind of high risk, we definitely want the machine learning model to be very robust. The diagnosis has to be absolutely no bias, and is able to provide some explanation, right? Why you make such a prediction. So yeah, so I think this is a very important topic or problem for medical application. Yeah, but that's a very good question.
That's a good question.
Yeah. Okay. Any other questions?
Dr. Chen,
Yeah.
so this application of adversarial robustness is beneficial when the noise is added to the image naturally, like like very naturally, because due to some transmission noise, if this image get corrupted, and we are building models against that robustness. But if some attacker wants to misinterpret this image, he can add like greater value of e value so that the model will anyways be fooled, right?
What's the last part of the question? Like,
Yeah. So if an attacker wants to make the model misclassify the image, he can try to add like greater value of epsilon so that the model will be fooled, right?
yeah.
So basically, with this current paper, like they are able to overcome the natural noise that an image may get when the user tries to take a picture with this mobile, or when he tries to upload the image to the app.
Yeah. So yeah, obviously there are different various type of attacks, right? So like I mentioned in the class, you can adding those noise perturbation, or you can have some structured patterns. So like physical attack, right? So you are not just adding to the digital image, you are actually print out the object, right? Or like those like one demo I showed, right? So those two people like holding a specific picture, right? And like you printed out like a T-shirt or hold up in front of the T-shirt, then the object detector totally missed the detection of the person, right? And also in image, typically we do some compression, right? So the natural image, any of the device, right? Your cell phone, I mean the camera, the cell phone, right? So you are doing image compression. So there's also possibility you can simulate some of the compression noise, right? For the JPEG 2000, so there's some blocking artifacts because they do the compression like block by block. So there's also possibility to injecting those kind of noise to mimic like a encoding decoding process of the compression algorithm. Also introduce these kind of perturbation attack. So there's various kinds of perturbation attack. Some malicious attacker can simulate and to break the machine learning system. So that's why now more and more people or researchers trying to improve the adversarial robustness by in the training stage, trying to generate these kind of adversarial example, right? So in the training stage, the model is able to learn something from these adversarial examples, but we don't alter the ground truth label, right? Even though we're adding some perturbations to the data, but we still have the ground truth label for that particular example. So the model is able to learn that to achieve better, adversarial robustness. So that's the idea for this robust training. Okay. Okay. Any other questions?
Yeah, I had a quick one. There's the different epsilon values for the level of like perturbation it adds. If someone were to just turn it up above what the model was trained on, would it make it so the model would fail?
The authors, I would assume so, because the authors actually like didn't really. This is another weakness. They didn't really elaborate too much on like that metric, the epsilon strength. So that's like one thing I was gonna also talk about. The model is actually just optimized on those. It can be obvious. It can like make sense as to understanding that the model was kind of optimized for those two strength values, right? The fluctuating. It was like 5 out of 255 and 16 out of 255. So I'm not sure as to what would happen with higher epsilon values, but yeah, I assume it would probably have some negative effects.
Yeah, if you have a large perturbation noise, right? So reach a higher level, I think the model probably will fail, right? Because when obviously you have more perturbation, then you'll make the model more vulnerable. So that's why you usually see those papers, they kind of evaluating their method under different epsilon levels, right? So yeah, so that's definitely if they perform these kind of more analysis on these different values, I think they'll be more comprehensive.
So I guess is the only way to protect against that without like training for higher epsilon is just to look at it. Like, is there a certain point where the images become obviously tampered with?
Yeah.
Yeah, go ahead.
Yeah, so I believe like it's obviously, if you train with like a higher strength, um, the model might be more like it might do better when it comes to like an even higher strength, like you mentioned. Uh, but if it's like obviously like messed, if there's literally visible noise, then yeah, like obviously, right, it would just obviously corrupt the model.
Yeah, okay. Any other questions? Okay, all right.
Did they mention like what loss function they are using to train this model, and also like what are just they are just showing that the architecture is a lattice architecture, but how are they using like the fully convolution layers, or how are they using the network?
So let me go back to this slide. So over here, right?
Yeah.
They don't actually go in. If you read the paper, I believe we have a paper review on this very research paper in a couple weeks.
Mhm.
But they actually like they don't really. This is another weakness. They don't explain like a lot of why they do certain things. Like for example, not only with like why the architecture is laid out like that, but why they used a learning rate of 10 to the negative third power or fifth power, or why they decrease the learning rate every 50 epochs. They kind of just choose all of these parameters and make all these decisions without any context or background, or don't really provide why they did that. The same thing as I mentioned, like they didn't really define how certain processes worked, like auto attack, or like why they used trilinear interpolation. They just kind of stated that they did. So it was kind of hard for like me as the reader to kind of understand why they did this or how everything worked.
Okay.
Okay, so I think we don't have much time left, so let's continue to the second presentation. So yeah, thank you again, Nikhil, for the great presentation. So let's
Yeah,
move on to the
of
next
course.
one.
Thank you.
All right, thank you.
Hello. My name is Crystal Ganya, and I'll be presenting Gloria, a multimodal global local representation learning framework for label-efficient medical image recognition. I'll start by discussing the motivation and goal of this paper. The motivation is that computer vision is able to conserve experts' time by automatically analyzing medical images and supporting clinical decisions. Obtaining large-scale labeled data sets is expensive and difficult, and these radiology reports require an expert to annotate, which makes them even more expensive and difficult to obtain. So the goal of Gloria is to develop a label-efficient multimodal medical image representations through the use of radiology reports. So Gloria's contributions are that it introduces a framework for learning global local representations for images using attention mechanism by contrasting image subregions and words. It demonstrates label efficiency and proposes a token aggregation strategy to handle abbreviations and typos, which are very common in radiology reports. So for the related work in radiology reports for medical images, they mentioned that previous methods have contracted labels from radiology reports using natural language processing instead of manual annotations. And in the absence of traditionally labeled images, this saves a lot of time. You don't have to go through and manually annotate each of these radiology images. Further related work in localized image text representation learning. Image text joint representation learning has been already used for tasks such as visual Q&A, image captioning, image text retrieval. And typically, these have used pre-trained models to extract image features. Typically, they have been pre-trained using natural images, which differ quite a lot from medical imagery. And some works have experimented with learning localized representations without using a pre-trained model. But again, these have only been done on natural imagery. The authors also wanted to look at zero-shot classification. They want to classify images without training labels, and this has been tried many times. Some have tried to utilize information from other modalities, learning visual representations using text as supervision. But all of the previous methods have learned global representations Gloria learns global and local representations, which allows additional information to be extracted from regions of interest. So as an overview of their method, the features are extracted from the text and vision encoder simultaneously. The global and local representations are learned by contrasting attention-weighted image subregions and words from the report. And then they are applied to downstream tasks with retrieval, classification, and segmentation being the primary ones. For an overview of the image and text encoding, the input is an image and text pair. The image goes into an image encoder. The text goes into a text encoder. The global and local features are extracted from both the image and text. The global features contain the semantic features that summarize the image and report. The local image features capture semantics in the image subregions, while the local text features capture word level embeddings. For the image encoding, they use a ResNet-50 backbone. The global features are extracted from the final average pooling layer of the ResNet-50 model, and local features are extracted from an intermediate convolutional layer, then vectorized to get the features for each subregion. So I cited this diagram that was provided by Jadiva, and the average pooling layer is where the global features are extracted, the final average pooling layer, and then the local features come from an intermediate convolutional layer. For the text encoding, they used a bioclinical BERT model pre-trained on the MIMIC3 dataset. The MIMIC3 dataset consists of 112,000 reports, and bioclinical BERT is similar to BERT, but initialized on biomedical texts. So word piece tokenization was used to minimize out of vocabulary embeddings in the cases where typos and abbreviations occurred. Each word of a report W is tokenized into N sub I subwords, resulting in N word tokens, which we can see in this formula here. And then here are what the word pieces actually look like. And I will discuss the word pieces in a future slide. For global and local representation learning, they learn the global representation functions, which relates an entire image to the matching report. And we learn local representation functions, which learns the alignment between image subregions and word pieces. It's simultaneously learning global and local representation allows for the model to perform better, which we'll see later. For the multimodal embedding framework, for each image, the global and local representation learning functions are trained to transform the features to representations in multimodal feature space. Global representation is a single D-dimensional vector. Local representation contains D-dimensional vectors for all M image subregions. And the word piece features are aggregated into word level features. So EFF fusion would become eFusion, and word level features are then projected into D-dimensional multimodal feature space using both the global and local representation learning functions. So they used a global contrastive loss, which maximizes the alignment between the true image text pairs. It allows for the correlation to be made between both images and the text. It maximizes the probability of the global image representation given its text representation, which would be this formula here, and it minimizes the negative loss posterior probability in this formula and maximizes the probability of the global text representation given its image representation in this formula. For the attention-weighted image representation, medical image regions of interest can be subtle. The global features can miss them. The attentions weigh different subregions of the image based on the significance of a given word, and attention weights are learned as part of the local representation by contrasting image representations with the corresponding word embedding. This allows for Gloria to bypass pre-trained models used for extracting image subfeatures. So they also used a local contrastive loss. So the localized feature matching function C is used to aggregate the similarities between all W word features T sub I and the corresponding attention weighted image subfeatures C sub I. And this is the formula for this feature matching function here. And then again, continuing to the local contrastive loss, the posterior probability is based on the matching function C. And this will be the primary difference between the global contrastive loss and the local contrastive loss here. It maximizes the probability of the attention weighted image subregion given its word representation in this local contrastive loss. And then it minimizes to ensure the representations are asymmetric to the input in this formula. For the total loss, the final training objective has both global and local contrastive losses. The losses are optimized jointly, which allows for better representations. And this is the formula. We can see the global contrastive losses are here, and the local contrastive losses are here. So it utilizes the global and local representations. We can look at this slide as kind of a general overview for their methods. So we have the image and text encoder, which are done in unison. The global representation learning gets the global image representation and the global text representation and learns them through a global contrastive loss. Meanwhile, for the localized representation learning, the image features are reshaped, the aggregate word features and the reshaped image features are projected into multimodal semantic space, then put into an image regions and word similarity matrix. Then the word-based attentionated weighted image representations and word representations are learned through a localized contrastive loss. So again, continuing. The global similarity is calculated based on the global image and text representations. The local similarity is calculated based on the localized image representation and word representations. And the final similarity is the average of the local and global similarities. So we can see here, this is where the global similarity is calculated. Here is the local similarity. And then the final similarity is the average of the two. For image text retrieval, we are given an image query. We want to output the matching text. Unlike previous methods, the authors use both local and global features to get a more accurate output. Using the previously mentioned matching function Z, the similarity between the image and sentences is calculated with consideration for the local representation, and the average of the local and global similarities gives the final output. For zero-shot image classification, we are given an image and we need to predict a label, but the classifier was not trained on the class labels. So the authors measured the similarity of the image text. The text possibilities were created by a radiologist and describe possible locations, subtypes, and severity of possible conditions. All text possibilities were projected into the multimodal embedding space using the pre-trained text global and local representation learning functions. The image global and local representations are obtained using the image functions, and the final output is the average of the local and global similarities. So to start with their experiments and results, I want to discuss the baselines they used. They compared their results to Convert, which is the state-of-the-art image text retrieval and classification model. It contrasts only global representations of image and report pairs, but the code was not available during the study, so Gloria's authors implemented their method. They also compared their results to DSVE, which localizes without object detectors, and VSE++, which is the best image text retrieval using only global representations. It does not contrast the global representations. So for the data sets they used, I'll start by discussing Chexpert, which consists of 224,000 chest radiographs from 65,000 patients. Each radiograph is paired with a radiology report, which is seen to the right. For Gloria, they focused on frontal chest radiographs, which reduced the number to 191,000 image text pairs. There were 202 expert labeled images in the Chexpert data set, and these were used as a test set. Then 5,000 images from the training data were selected for validation. Then the authors created Chexpert 5x200. It is very similar to the Chexpert 8x200 retrieval dataset that was created by the authors of Convert. It is 200 images from 5 positive tasks, which include a partially collapsed lung, enlarged heart, consolidation or fluid in the lung, edema, excess fluid, and pleural effusion, fluid around the lungs. Each image has only one positive label, which helps reduce the confusion from zero-shot classification. We can see some of the tasks that they were looking at to the right. So continuing, there were 2 more data sets they used to evaluate their methods, which is RSNA pneumonia, which is 30,000 frontal view chest radiographs with 2 labels, either healthy or pneumothorax positive. Their train validation and test was a 70-30-30 split according to the paper. And SIIM pneumothorax was 12,000 chest radiographs paired with manually annotated segmentation masks for pneumothorax, with again a 70-30-30 trained validation test split. So to begin with, to begin explaining their results, I want to explain this is a precision at K metric, which is a top K precision metric. It's relevant items over viewed items K, with K being the 5, 10, and 100. They check if the selected report belongs to the same category as the query image, and that's how they calculate this. It was trained on Chexpert, and this is the average. These are the average of 5 runs. So when we look here, we see DSVE performed the worst out of all of these methods, regardless of the top K metric. VSEE performed slightly better. Then one of the things is that Convert is the current state of the art, and it performed very, very well. And actually, something that should be noted is that Gloria and Convert have very similar results when Gloria is only using the global only version. But when they apply both the global and local methods, they end up outperforming the previous state of the art by 3 to 4% across the board. And we can see here that they very much outperformed Convert. Then they did a fine-tuned classification. So these are randomly initialized weights, and these would be ImageNet initialized weights, with the rest being initialized with pre-trained rates from the representation learning step. We can see here that the randomly initialized weights did quite poorly. Surprisingly, however, DSVE and VSE both did worse than randomly initialized weights, but the ImageNet initialized weights did very well. And then Convert and Gloria performed both very well, and in some cases it was very close, and Gloria on the RSNA dataset very much outperformed Convert with the entire data set being utilized. So then for the zero-shot classification, we can see that when trained using Checkspert and evaluated on Checkspert 5x200, the zero shot, Gloria zero shot does the best, even better than when they fine tune it on the entire Checkspert 5x200 data set. The sensitivity is better, but the specificity is worse when fully trained or fully fine tuned on these. And overall, the zero shot performance was very well. For the RSNA data set, the fully fine-tuned data set or fully fine-tuned model did perform better than the zero shot method. However, we can see that the zero shot method was still very much competitive with some of these, with the more fine-tuned model. Then for segmentation, we can see the DICE score here, which is the similarity between these two samples, and these percents are the amount of training data used. It used a UNet architecture and was initialized with weights from Gloria's pre-trained image encoder. We can see that the ImageNet initialized weights actually performed the best when the entire training data set was used, but Gloria performed the best in both of the low labeled or the small data sets. So then I want to discuss the word piece attention weights. The attention weights were arbitrarily associated with word pieces. So we can see in this case, E was the primary thing for this attention here, with the double F and the Usian not having any attention associated with them. Then the attention weight in the next one was not associated with the E, but was instead associated with the double F and the Usian. And this trend somewhat continues. But then token aggregation is applied, and we can see that this more or less focuses the attention across the entire set of word pieces. So the model is paying attention to this piece here for the word pneumonia, and paying attention here for pneumothorax, paying attention here and here for edema, and here for opacity. Then for image text retrieval, we can see that Gloria once again outperforms the previous methods. One of the things I want to note again is that Convert and the global loss only version of Gloria perform identically, and that is because Gloria's main contribution is this local loss. Other than that, with an RNN text encoder instead of the BERT encoder, it performs quite a bit worse. Without token aggregation, it does lose quite a bit of its precision. The local loss only did perform worse in these cases, and using only the global similarity or local similarity did reduce the results by a fair amount. For zero shot classification, again, Gloria once again outperforms all existing methods with the exception of specificity on VSE++. And this, again, we can see Convert and the global loss only perform identically. And again, we can see that in general, each piece of Gloria is important in order to get an improved result. That taking away the token aggregation does drop the results. Only using a local loss drops the results. And so on. All right. In conclusion, focusing on local features in addition to global features improves the model's ability to learn. This reduces the label requirements. Contrasting with other samples improves the results, and at least in the case of medical imagery. Then I want to discuss the strengths of the paper. It improves upon previous methods through the use of local attention. Zero shot capabilities are quite impressive, And the experiments are thorough and show how each piece affects the results. And the clarity of the paper is very good, and the authors go into a good amount of detail with their methods. For their weaknesses, I wanted to point out that they only use chest radiographs, and it made me wonder how would it perform on abdominal or head radiographs. The novelty of the paper is relatively low. Previous works have used local representation, but not on medical images. But also, for the most part, this implementation is Convert, just with local representation added. In fact, Convert even uses BERT and ResNet 50 as its encoders. So there was also a notable omission of the compute costs, which definitely made me wonder, computing both local and global attentions is bound to be more expensive. So how much more expensive is it? What is the cost accuracy trade-off? And the overall NIPS rating, I would give this paper a 3. I would generally vote to accept it. The results are very good, but the lower novelty and omission of the computation costs hold the paper back, in my opinion. And here are my references.
Okay, so that's it, right, Crystal?
Yes.
Okay,
Yes.
all right. Yeah, thank you for the presentation. So yeah, I'm glad you select this paper, because we didn't talk about this kind of multimodal in the class. And actually, this is a very emerging topic, not just for the medical, in the computer vision field as well. So you see right now, the vision transformer, right? The transformer architecture which originated from the language NLP field. And then researchers from computer vision adopt these transformer architecture to the vision task. So we now have vision transformer. And then now people kind of using all these vision transformer architectures for various tasks, right? So basically you will see a lot of works using vision transformer instead of using the traditional CNN. And also because of the uniformity of the structure, right? So then we can, using a single unified architecture, these transformer architecture that process language or text and the visual data, right? So now you see a lot of foundation models using multimodal training. They're using text and they're using images or videos to train a transformer foundation model that can be applied to any modalities, right? Say in the deploy stage, you only have vision data or you only have text data, but you're still able to deploy a single architecture. And of course, if you have multimodal input, then the learned representation is going to be stronger, right? Because language has very rich semantic information, right? Compared to images. Natural images has a lot of redundancies, but words, which is human developed, right? So there's a lot of rich semantic information there. So these kind of multimodal learning will enable the model to learn very strong representation capability. So I think, for this topic, medical, like a report generation or text to image retrieval is a very interesting topic in the medical field. As if you look at the MICAI conference papers, there's a lot of papers they are doing is using AI algorithm to generate those like a medical report, right? To help physicians to facilitate or reduce their burden. Maybe they only have to look at the report generated by the AI algorithm to correct a few things which may be not clear or maybe some error there. So I think there will be has a very good application value. Okay, so that's my general comment about this topic. And also, I think some of the things you mentioned are valid, especially the weakness. it seems like this paper, their proposed method is just adding the local representation, right? The global representation pretty much has been used by many existing work, right? The covert,
Yes.
what is the
Convert.
method? Yeah, that method using the global, and based on the result, you see they pretty much achieve identical result, right? It's just their local representation give us some extra boost in terms of the overall performance. But I think the motivation is simple, straightforward, right? We want to some of local attention to capture some important or salient regions, especially for the image and also some of the words, right? Salient information there. But yeah, in terms of technical contribution, like how these global and the local information are going to, affect each other or have a better learning is not, there's not much new thing there. They basically just have these kind of two losses, right? The global contrastive loss and the local contrastive loss. But in terms of the same technique applied in the global sense and the local sense. And also for their formulation, I was kind of wondering, for their loss function, they have like equal weights, right? For the local and the global. So if you look at the loss, right, 4 terms, there's no like weights or coefficient in front of them. So I'll be interested to see like, is it global more important or the local, right? So how is it possible to have a learnable weights to better determine, right, how much contribution these global representation and the local representation will play a role for different input. Yeah.
And I thought that was really interesting because like in this diagram right here, it's the global loss that is more important than the local only loss.
Mhm.
But when they actually talk about it in terms of, I believe this being the representation, it's the local only that's more important than the global only.
Yeah. Yeah, so I think this one, but these are different tasks, right? So this is image to text retrieval, or what is the previous one? That's the classification.
Yeah, it's right here. There's also image text retrieval, but
Yeah.
these two were, so this
Yeah.
is the 0-shot classification, but these two were actually taken from the supplementary material and they never discussed these side by side,
Yeah.
which might be a bit of a weakness. They
Yeah,
didn't
it's
explain
kind of strange. Here it shows global loss is more important than the local, right? Based on the result. But the other one is kind of show like a different opposite.
And I think this might be representation and not losses. That might be the only difference. But they didn't explain it well because they're taken from two different
So I think
portions of their paper.
This one maybe needs more analysis, right? More discussion, right? What, how exactly, different representation, plays a role in the final performance. So that's maybe one thing I noticed, based on the result in the presentation. Okay. So any other questions?
Yeah. So I just had quite a simple question, to be honest. So this K metric, your top K precision, does or like do the authors kind of like elaborate what does this K represent exactly?
So this is what the authors said about it. They checked if the selected report belonged to the same category as the query image. So every time this was true, relevant items went up. And then for the 5 that they viewed, this
Yeah, so Yeah, in general, this top K, because you're doing retrieval, right? So let's say top K means you retrieve the five, you retrieve, you can retrieve those images, right, based on the similarity, right? So that's the retrieval. You compute, you have a query, right? Then in the reference database, you compute these feature embeddings and you compute the similarity. And you can rank these retrieved items or images, right, based on the similarity, right? So the top one will have the highest similarity, right? If you only care about one retrieval, right, then you should select the top one because that's have the highest similarity, right, which corresponding to your query. Here, the top K means you can select K of them. K can be 5, 10, or 100 from the reference database. If any of the ground truths is in that K, and you are considered this is a success. Okay, let's say I give you, select top five. Okay, if the ground truth is in that top five, may not be the top one, right? So the correct one could be like the fifth, right? Ranked at the fifth based on the similarity, but still it will consider this is accessible retrieval because I allow you to have like 5 choice, right? But the ground truth is in those top 5. So then you can think about like top 10 is 100 is gonna be you have like 10 or 100 choices.
All right. Yeah, thank you. That makes sense now.
Okay.
Wait, is this right here a chart of top or K precision? The thing that you're talking about? Well, I'm just confused
Yes.
because the at 100 is a worse score. Shouldn't it be a better score because it's easier based on what you said?
Yeah,
It
so here, I don't know why. Is it different?
I think it's because they have 100 choices. It's like that's the case for all of them. So they viewed 100 items, and out of those 100 items, less and less of them were relevant as the number increased. So there are 5, they viewed 5 items. Well, this is the number of relevant items, like 4 of them, 3 of them. And then they viewed 10 and 7 of them were relevant. And then they viewed 100 and only 53 of them were relevant. That's how I understood it.
Yeah, I think this might be a little different than the normal like top K.
Yeah. So this is
Okay.
different, right? So the one I just described is the normal top K, like in the retrieval literature. So that's why you will see typically you have like more K is larger, then you end up with higher accuracy because you are giving more room for error, right? Yeah, so I think here you guys can go back to the paper and see how they define these metrics. And yeah, this is definitely important for you to understand, right? How the different K will affect the performance if these the trend makes sense. Okay. Any other questions?
I have one. I just was wondering if you could quickly again explain the difference between local and global representations, just so that I'm clear on what the difference actually is.
So the global representation is going to be like the entire image, and the global representation of the word is going to be like the entire sentence. And then the local representation of the image is going to be like the image features, and the local representation of the text is going to be like the word pieces, these.
Yeah, Crystal, maybe you can go to slide, is it 15? Can you go down the slides?
Yeah.
No, keep going down. I think there's a one figure. Yeah, 18, I think 18. Yeah, maybe you can explain here, right? So they have these global representation, right? So you have this, the horizontal, those two arrows, right? So you have an image encoder, which look at the entire image, right? The text encoder is look at the entire sentence, right? So you capture those global information. So how can you explain how the localized representation here, right? How these like a locality is being learned from here, right? So how do they generate?
Okay, so it's the aggregate of the word features and the the reshaped image features go into the multimodal semantic space. They go into the image region and word similarity submatrix. Then the word-based attention weighted image representations and word representations are both learned through the contrastive loss. Whereas this is just the whole image and the sentence. These are the word features, like the word pieces, and the image features that go into all of this. Is that?
Yeah, so I think the if you look at the text, right? So the global will basically, you kind of collapse all the there is like 4 color, right, indicating 4 different words, right? So they basically consider all of them. But for the local representation, so they have the keyword of like word representation, right? So basically you have a representation for each word, right? So that's considered like the local, their so-called local representation. So similarly for image, right? So you have these reshaped image feature, right? And it can kind of attend, you also have these kind of attention from the word, right? So how these different words gonna have some effect on the image region, right? So I think in one of the illustration you have like ammonia. I mean, is it effusion or? Yeah,
right
effusion,
here.
right? So you have different. Yeah, this may be no words, right? This is just letter. You have another figure like have pneumonia or like opacity. They have different, have a different attention on highlight like the local region, right? So where that specific region is corresponding to the a paired image. Yeah. Okay. Any other questions? Okay, so if you don't guys have any questions, we're gonna end here. So I think this is a very interesting topic. So if you guys are interested in this kind of multimodal learning, you can maybe read some of the reference mentioned in this paper as well. So that will give you some overall picture, right, in this field. Okay. One quick reminder. The programming assignment, I think, is due March 25th, right? So that's for the MI brain tumor segmentation. So if you haven't started, please go ahead. You still have like 10 days left. So I highly recommend you work on this because training the model may take some time, okay? So other questions before we end the lecture? Okay, great. So we're gonna stop here, and yeah, thank you for the 2 presenters for the presentation, and we'll continue discuss the other 2 2 papers on Thursday. Okay. All right. Thank you, everyone. Bye.